Hi, I'm Seung-Ho Baek, and I'll introduce our paper titled Graph-Assisted Stitching for Offline Hierarchical Reinforcement Learning. This is a joint work with Taegan Park, Jongchan Park, Seungjun Oh, and Yoosung Kim. Offline GCRL aims to learn a multitask policy that can reach diverse goals using a pre-collected dataset. This paradigm offers two key advantages, especially for real-world applications. First, offline learning does not require any additional interaction with the environment. Instead, it relies solely on previously collected offline data. This paradigm is particularly effective in scenarios where online data collection is expensive, time-consuming, or even risky. Second, while standard offline RL typically focuses on learning a policy for a single reward function, offline GCRL enables learning a policy that generalizes to a wide range of goals. In summary, the key objective of offline GCRL is to train a goal condition policy that can solve multiple tasks using a static dataset. However, offline GCRL faces a fundamental challenge in tasks that require long horizon reasoning. In such tasks, rewards are typically given only at the end of the episode, forcing the agent to learn from sparse rewards. This makes it difficult to provide clear learning signals, especially when the current state is far from the final goal. To mitigate this challenge, offline HRL adopts a two-level decision-making framework. The high-level policy generates sub-goals, and the low-level policy executes primitive actions to reach them. This hierarchical structure decomposes complex long-horizon problems into manageable short-horizon subproblems. As a result, it has the potential to improve learning efficiency even in sparse reward environments. Now, let's talk about why trajectory stitching is crucial in offline HRL. Offline datasets often consist of diverse trajectories collected in attempts to achieve various goals. As shown in the figure, each trajectory begins from a different initial state and progresses toward a specific goal. By stitching partial segments from different trajectories, we can create long horizon trajectories not originally present in the dataset. This stitching allows us to leverage transitions that were not observed within a single trajectory, significantly enhancing the agent's long horizon reasoning and goal generalization ability. However, most existing offline HRL methods lack mechanisms for cross-goal stitching, which limits the high-level policy's ability to compose effective sub-goal sequences. This limitation becomes particularly critical when the dataset consists of short goal reaching or suboptimal trajectories. To address these limitations, we introduce GAS, a novel offline HRL framework that eliminates the need for explicit high-level policy learning. Instead, GAS formulates sub-goal selection as a graph-based approach to enable efficient long-horizon reasoning and state transition stitching. GAS consists of four main stages. First, the TDR network is pre-trained from the offline dataset. This representation is then leveraged across all subsequent stages, including graph construction, low-level policy training, and task execution. Second, we compute the TE metric to filter out low-quality states and use only high TE states to construct the graph. Third, the low-level policy is trained to reach directional subgoals using the TD-aware subgoal sampling strategy. Finally, given a final goal at test time, the graph uses a shortest path algorithm to generate a subgoal sequence. Then, the trained low-level policy executes primitive actions to reach each subgoal along this path. So far, we have provided an overview of the GAS framework. Next, we delve into its four key components in more detail. Let's start with the first key idea, temporal distance representation. Recent work proposed a method to learn a TDR from offline datasets for reinforcement learning. In this representation space, the Euclidean distance between two embedded states corresponds to the minimum number of steps required to transition between them in the original state space. To train the TDR, we leverage the equivalence between temporal distances and goal condition value functions. Specifically, we use an IQL-based goal condition value learning scheme, where the latent space is optimized to preserve the optimal temporal distance between states. As a result, the learned space captures and preserves global long horizon temporal structure in the original MDP. Next, we introduce the concept of temporal efficiency. TE measures how well the actual transition aligns with the optimal direction at a fixed temporal distance. More specifically, given a current state, we compare two future states within the same trajectory. The actual reached state is the one observed after HTD steps, and the optimal future state lies at a temporal distance of HTD from the current state. If the trajectory was collected with optimal behavior, these two states are expected to be close in the TDR space. In contrast, suboptimal trajectories often lead to large differences between them. Based on these two states, we compute the cosine similarity between their direction vectors to obtain the TE value. A higher TE indicates that the actual transition is well aligned with the optimal direction, and the corresponding state is considered a high T state. Before graph construction, we filter out low T states across the dataset and use only high T states as graph node candidates. This TE filtering strategy not only improves graph quality, but also reduces graph construction overhead. Next, we introduce the TD-aware graph construction process. First, we cluster states in the TDR space at regular temporal distance. The clustering procedure is straightforward, as shown in the algorithm. If a candidate state is farther than a predefined threshold from any existing cluster center, we create a new cluster. Otherwise, the state is assigned to the nearest center. This clustering allows us to group semantically similar states from different trajectories. Then, each cluster center becomes a graph node, and we add edges between nodes if their temporal distance is below a predefined threshold. This enables natural cross-goal stitching across disconnected trajectories and facilitates effective long-horizon planning. Lastly, let me explain how we sample subgoals for training the low-level policy. We select a subgoal at a fixed temporal distance from the current state within the same trajectory. This ensures that the subgoal horizon is aligned between training and actual task execution. To improve the generalization of the low-level policy, the selected subgoal is transformed into a relative direction vector. Then, we train the low-level policy with this direction, using a modified DDPG plus BC objective. Now, we present the experimental results on the OG bench and D4RL benchmarks. These benchmarks cover diverse dataset types such as locomotion, stitching, exploratory, and manipulation. Our experiments are designed to answer 4 key questions. First, let's evaluate the agent's long-horizon reasoning ability. AntMaze Giant Navigate and Scene Play require substantial long-horizon reasoning capabilities in the navigation and manipulation domains, respectively. As shown in the table, GAS achieves strong performance on both tasks, showing that our graph-based subgoal selection enables effective long-horizon planning across diverse domains. Next, let's evaluate the agent's stitching ability. The AntMaze stitch datasets consist of short goal-reaching trajectories, requiring effective trajectory stitching for optimal planning. AntMaze Giant Stitch is the most challenging benchmark, requiring substantial long-horizon reasoning through effective trajectory stitching. As shown in the table, GAS consistently outperforms all baselines, with a notably large margin on AntMaze Giant Stitch. This demonstrates that our TD-aware graph construction effectively facilitates trajectory stitching. Now, let's evaluate the performance on suboptimal datasets. The AntMaze Medium Explorer and Large Explorer datasets contain extremely low-quality data, consisting of random exploratory trajectories. As shown in the table, most baselines fail to learn meaningful policies in such datasets. In contrast, GAS achieves strong performance, effectively learning from suboptimal data as long as the dataset has sufficient coverage. Finally, let's evaluate the performance on image-based tasks As shown in the table, GAS consistently outperforms all baselines, not only in state-based environments, but also in pixel-based settings. This demonstrates that the GAS framework can be effectively applied to pixel-based environments as well. To summarize, we propose GAS that leverages a graph-based approach for sub-goal selection without requiring explicit high-level policy learning. It demonstrates strong performance across 4 key abilities: long horizon reasoning, trajectory stitching, learning from suboptimal data, and handling image-based tasks. For more details, please check out our paper and project website.